Okay, welcome to this session. So in today's session, we will see example of power flow analysis using Gauss sidel and a neutral Raphson for a typical three-bus system. So in this example, we have three buses. One is a slack bus where the voltage and the voltage angle will be specified, whereas both power will be calculated. Again, we have a PV bus system where active power and the voltage magnitude will remain constant. And again, we have a load bus, PQ bus. In this case, we'll have a fixed magnitude of load, whereas voltage and the voltage magnitude will be calculated. So the general representation of this diagram indicates that we have impedance from bus 1 to bus 2, from bus 2 to bus 3, and from bus 3 to bus 1. So it's easy to make a Y bus admittance. In addition, the general specification indicates that we have set of voltage for both PV bus and the slack bus, which is unchanging. But in addition, we have a constant voltage angle for slack bus, whereas we have fixed load for PQ bus. And on the diagram, the representation indicates that this legend is used to represent the one line diagram. So it's easy to remember the power equation for uh, a finite bus or n bus. So in our case, to make the calculation simple, we don't have a resistive part of both generator internal impedance as well as a transmission line. We ignore that. So for the our equation also for active power, we can ignore this part because this part we don't have any conductance. We ignore it because for simplicity. Again, for reactive power also, we don't have a conductance part. So the equation is reduced to this representation. So try to recall this for uh, this the equation for Pi and Qi as it will be used for to obtain the magnitude of the power at required bus based on the iterated voltage. In addition to that, by considering this equation, we'll form a Jacobian matrix as a partial differentiation of the equation for a neutral Raphson. So proceeding to Y-bus matrix formation, very simple and straightforward. The pi-was is obtained for a diagonal matrix is the summations of all admittance connected to the bus. So for a bus 1, we have Y1, 2, Y13. So if we add this force, we'll get minus 8.3. Again, for bus 2, we are also a total component added up to give us the summation of 5 plus 4 is 9. Again, for by 3 also, y13 and y23 is added up to get 7.3. Whereas when we come to off diagonal matrix is the negative of the admittance between a bus, so that, for example, for y12 we have minus 5j, then y12 or y21 will become 5j. It's 5j. y12 is equal to y21. y13 is equal to y31, like that. It's very simple and straightforward. So we can use this for iteration to obtain voltage, current, and power equation at required bus for Gauss sidel method. So at a flat start, whether it's Gauss sidel or Newton Raphson, one thing is that they have in common is that we'll start with a flat start initial estimate. For all three bus, for example, for slack bus, we have this, which is unchanged, both angle and the voltage. For PV bus, we have V magnitude is unchanged, but the angle can be calculated by taking the calculation of V and taking the variability of angle. Again, when you come to PQ bus, both voltage and angle will be calculated. But at initial start, at what you call flat start, we take this magnitude. In addition to that, for a bus 2, since it's a PV bus, the power is specified. Active power supplied by the generator is taken as plus 0.5 per unit. Voltage also specified, but we are going to vary the angle. But when you come to PQ bus, since it's a load bus, will take the negative of the given parameter. That means it's consuming power. So we have minus 0.8 per unit and minus 0.3 per unit. Taking this consideration, we'll go to the Gauss-Seidel iterative method. So the general representation of a voltage equation based on the equation previously obtained for a power and voltage relation. Voltage is at any bus, voltage at I bus after Ki iteration is obtained by using this equation. So I means it's diagonal math, Y bus connected to that. Whereas Pi and Qi is the power at that bus, Vi at K conjugate. This is K iterate obtained voltage and conjugate, and the summation of Yi Vj Ki or K, because one thing is that we have to remember for the news Gauss-Seidel is whenever there is new update available, we'll use immediately. That's why it says K plus 1 or K. For example, we have 3 bus voltage. For first iteration, maybe we'll use a flat start. For second bus voltage, already we get first bus voltage for a new, then we'll use that. Again, if we go for third bus, PQ bus, we'll use updated voltage for bus 1 and the bus 2. That means that's the meaning. Why you call is K plus 1 or K. For example, if we have more than 3 or more than something like higher number of buses, then we will use readily available voltage estimation for an next. For example, we have 5 voltage. Then uh, if we calculate the first bus voltage, we'll start a flat start. If we calculate second voltage, already for the first bus we have a new one. Then that we use readily available updated voltage. That's the meaning of that. So to carry out for a bus, PV bus, we'll compute Q because we don't have Q for a PV bus. We have equation for a Q, which is stated on slide 1. By using that, we'll calculate the magnitude of a Q, Q2 for first iteration. Then update V2 magnitude 2. This already by using that, we'll calculate a voltage magnitude for PV2. Already slack bus voltage and angle is the same. But for a PV bus, the voltage magnitude is the same, but angle will be vary. But to obtain that angle, we calculate the voltage magnitude for a PV bus and keep the magnitude as the original given value, but we'll take the angle. So we'll update that. Then for a bus 3, we'll use the already we have Pi and JQi, which is a load. We have all other parameters except we'll use updated value of voltage. Means for slack wire, there's no any updation for voltage angle. But when we come to PV bus, we have updated voltage with a constant magnitude at a new angle. So we'll use that to calculate a voltage after first iteration. Now what we'll do? Then for a second iteration, we will calculate the voltage 2 by calculating a new value of reactive power by using updated voltage. Then we'll go for calculation of voltage. Then we'll keep the same magnitude of voltage, but we take the new angle. But when you come to the third bus, again we have all parameters except we'll use a new updated value for bus 2 voltage, whereas for bus 1 and the bus for bus 1, both voltage magnitude and voltage angle will be the same. So after three iteration or after 4 iteration, the magnitude of the slack bus voltage and angle is the same, but for a PV bus, the magnitude of the voltage will remain the same, will not change that, but you will see that the angle is changing and it will take a new angle. For a bus 3, the voltage is calculated like this after 4 iteration. So the stopping criteria for a new for a Gauss sidel is taken as the ratio, not the ratio, the magnitude of the change in a parameter. For example, we can take a voltage 3 magnitude or voltage 3 angle or the voltage at bus 2 angle. So by considering that, we will stop the iteration when the magnitude of the variation between each step is less than tolerance value. So, for example, here we consider the all parameter like this. So what we are varying is this parameter is varied angle for bus 2 voltage 3 magnitude angle for voltage 3 like that. So if we consider that, for example, here the voltage magnitude, is changing from 1 per unit to this, so the voltage magnitude variation is 0.094. So this greater than the tolerance. Then we'll go for the next update. Again, we see that the voltage is changed to this. Again, the voltage magnitude variation from the first iteration and the second iteration like that. So we'll go like that, and finally we'll reach where the change in voltage magnitude is less than this. At that time, that's the termination criteria for a Gauss-Seidel method. So, like Gauss-Seidel, we have 3 state variable here. The bus voltage angle for bus 3, bus voltage angle for load bus, as well as the voltage magnitude. So considering this state variable and taking the 3 specified parameters as a mismatch equation, specifically for a PV bus, we have specified power and voltage. So we consider magnitude of P at bus 2 at specified and should be remain constant. So the mismatch is obtained by taking the difference between specified and calculated. Every time we calculate the magnitude of active power as bus 2, at bus 3 and the bus 3, at bus 3, and we take the difference. This is called a mismatch equation. Finally, after we obtain that, we'll solve an equation what we call J times X is equal to change in S. Jx is a Jacobian matrix. Change in X is a correction value for this state variable, whereas change in S is the change in a specified value. For example, for bus 2 we have a fixed P. So change in this mismatch is obtained by taking the difference between a specified value and the calculated value, as well as for a bus 3 we have a fixed active and a reactive power. We can obtain the mismatch by taking the difference between a specified value and the calculated value. So considering those 3 state variables, three specified value and change in specified value, we can go to the Newton-Raphson algorithm by using this equation. So after we obtain the Jacobian matrix, change in X is already change in state variable, change in S means change in specified value. So we will solve for the value of change in X with a correction factor. We will add a correction factor to a previously estimated value and we will get a new updated value. So to do that, first we calculate a Jacobian matrix at the start or flat start. For example, in our case, for initial start, we guess the initial parameter. Already we have done it. And we take the specified value, change in specified value by calculating the magnitude of a power at bus 3 and the bus 2, and we'll take the difference between a specified value and the calculated value. So that will be a change in S, and we'll calculate change in IX. Then we update the uh, state variable by using this change in specified value and uh, obtain the correction factor. So initially we have a flat start for this state variable, but we obtain the correction factor by using this equation, and after this iteration, a new state variable will be obtained by adding the initial estimated value with change in state variable. So again, we will calculate the mismatch. The mismatch is obtained for P2, the active power at bus 2, P3, active power at P3 and Q3. So by considering that, if the mismatch is greater than the tolerable error value, again we'll go to the next iteration. When we go for a next iteration, we will calculate a Jacobian matrix with a new updated value. Then we calculate the magnitude of the specified variable with a new updated value. Then we'll check obtain change in specified value by taking the difference between originally specified value and currently updated value, which is obtained by taking the calculation. So by solving again a new change in X, which is means correction factor, again we'll update the state variable. So after several steps, for example, this is the three-state value sigma 2, sigma 3, V3. Initially, we guess the magnitude of voltage angle as 0 and the magnitude of voltage as 1 per unit. So during that, the power mismatch, maximum mismatch is obtained. So here, what we'll do is that we calculate sigma 2, sigma 3, sigma by using first iteration, changing mismatch. Mismatch is obtained by taking the specified value and calculating the space magnitude of a power as that uh, bus by using the flat start and take the difference. So like that, the voltage is calculated like this and the mismatch is obtained. Then again, calculate the error like that we'll do. And finally, after step 3, we obtain this magnitude of error, which is less than the specified value. So considering this, it's very easy and straightforward to use the magnitude of obtain magnitude of the parameter after several iteration using both Gauss sidel and Newton-Raphson. But what makes those two approach different is that Gauss sidel is used for linear and this Newton-Raphson is very important to obtain nonlinear system, specifically for a power system. You see change in mismatch like power and voltage angle, voltage is nonlinear, so it's very useful for such types of equation.